All right. So the last thing we talked about was the um, overlap, homo-lumo overlap in the 4+2 cycloaddition, and how the orbitals, the size of the orbitals have to match. And we also talked about how that p orbital is actually a graph of the equation of the path of an electron around the nucleus of that particular atom. And we also talked about the necessary conformation for the 4+2 cycloaddition to actually happen. And that is that the diene must be in the S-cis conformation. Right. So we talked about that. And we talked about some special cases where you wouldn't see cycloaddition, and as in the case here, where the diene up in the top structure is locked and there's no rotation around the sigma bond that separates the two pi bonds, so you can't get into S trans. You can only adopt S trans and not S cis. And we also talked about another scenario where, due to steric hindrance, the diene that's shown here, hold up, let me get this out of the way, won't react because the two methyl groups would prefer to be away from one another. All right, so the rest of the concepts deals all the cycloaddition we can discuss while working through some examples. So let's go to here. We're going to just do some basic examples, and then I'm also going to highlight some other characteristics of the reaction while we're doing these examples. So the top example is very basic, and it's just asking us to predict the products. All right, so all we're doing is predicting the products. That's it. Excuse me. And how do we do that? Right? If you want, we can keep our numbering system in place. So this is 1, 2, 3, 4, and we'll number this one 5 and 6. And remember, the key to working through these 4+2s is to understand where the bonds are being formed, where the bonds are being broken. So we know that there's going to be a bond formed here between 1 and 6, if we have it numbered this way, like this. We know there's going to be a bond formed between 4 and 5. And we also know that there's going to be a new pi bond here between 2 and 3. Right? So we put the arrows in for the mechanism. It's the same 3 arrows, no matter what your diene is, no matter how it looks, how many substituents are attached to it, it does not matter. The arrows are going to move in the same pattern, no matter what. So you're going to go from here to here, like that, to illustrate that bond being formed. And it's the electrons in the pi bond that are going to be used to make that new sigma bond. And then these electrons here from this pi bond are going to come here like that. And then I'm just going to shift this pi bond to here, right? So in the product, we're going to get a 6-membered ring like this with a new pi bond right here. Right, and if we number that, we'll see that it's the same carbon, same atoms, everything. 1, 2, 3. Sorry about that. 3, 4, 5, 6. Right, so that anytime we do a cycloaddition, and it's a 4+2, just think about it in practical terms. That 4+2 = 6. So if you do a 4+2 cycloaddition, you're going to get a 6-membered ring as the product. All right. Any questions about that? All right, let's do the next one. So again, this is my diene. This is my Dienophile. Right. And when I react those two together, am I doing something different here? Anything going to change as far as the mechanism is concerned?
No.
No. Same arrows, Same 4 plus 2, different product. So we're going to push these arrows here. I'm going to take this pair of electrons in the pi bond, move it here, and move this here. So on my product, we're going to get a 6-membered ring. Let's number them. 1, 2, 3, 4, 5, 6. 6-membered ring in the product. And this is 1, 2, 3, 4, 5, 6. And then on atom 2, over here, we have a methoxy group attached to that. So we can put that in. Let me erase this right quick. We can put that group in here, OCH3. And then on atom 6, we have a bromine. And I'll come back and put the numbers back. What you can see right here on atom number 6, we have a bromine. So we're going to put that in the product. And then also we need to remember that the double bond shifted between 2 and 3. So this is 2, this is 6, and my double bond is now here. Any questions about that? All right, and then I know we talked about stereo specificity, but in this particular case, right, this is a chiral center of where the bromine is. All right, so right here, that's chiral, but there's no bias, right? There's no way to favor one product over the other one. So in actuality, you'll get both stereoisomers. So you'll get the wedged stereoisomer, and then you'll get, let me just copy that. The dash stereoisomer. All right. So can somebody tell me how we could force this to be chiral and force one of these to be favored over the other? Sorry about that. Let me fix that right quick.
Is it by rotating it?
Say that again.
Rotating it?
Rotating it in space is not going to change the chirality. It's just going to change the orientation. Remember when we talked about how to generate chiral centers? There are 2 ways you can do it. One way is to start out with something that's chiral and react it with something that's achiral to get an unequal mixture of stereoisomer. The other way is to use a chiral catalyst, right? In the absence of either of those methods, if you set a chiral center, it's going to be racemic, right? You're not going to get one favored over the other. It's just going to be a racemic mixture. All right. One other thing about this reaction is, if you notice on the diene, the OCH3 group is what we consider a donor. It's an electron donor, right? And so if you have for your diene, if you put a donor on it, like OCH3 or some other atom that has lone pairs that it can donate towards that pi bond, then what happens in this case is you actually increase the rate of the reaction. So on your diene donors, increase the rate if it's on the diene, not if it's on the Dienophile. Because if you remember, your diene is electron rich. So if you make it richer by adding a donor, it's going to make the rate, it's going to increase the reaction rate. And by the same token, on your Dienophile over here, you have bromine, which is a pretty moderately electronegative atom. And most of the times when we think about halogens, we think about them as electron withdrawing groups and not donors. So if you have an acceptor, I'm just going to call it EWG. And this is short for electron withdrawing group. right? This is going to increase the rate for the dienophile, right? It makes the dienophile more reactive. So if you put an electron withdrawing group on your dienophile, it's going to make it more reactive. Just like if you put a donor on your diene, it's going to make it more reactive. All right, so let me put that down here. And this is all a consequence of the homo-lumo overlap, right? These things affect the energies of the HOMO and LUMO, and they make them either more accessible to one another, closer in energy to one another, or further apart. So I'm going to put that here, that electron withdrawing groups increase the right. So if you put an electron withdrawing group on your dienophile, it's going to increase the rate of reaction. All right. Questions about that example? Let me put it in here because we talked about it. Go ahead.
Can you re-explain why we have the wedge and the dash for the bromine again?
Yeah, it's a racemic mixture because there's no bias to make one of those products favored. Right? You can, like, let's say if I started with on my diene and I had some substituent that had a chiral center attached to it, right? Obviously, not the sp2 carbons and the double bonds can't be chiral, but if I had a group, let me just see if I can squeeze it in over here. If I had a group like this, right? So if I had this as my diene and the substituent, instead of being instead of being the OCH3, it was something like this, where you had a chiral tert butyl group attached. Then that's going to create a bias, right? Because remember, anytime you have, let me move this over so I can make it look more professional and not like a third grader drew it, right? But anytime you have let's just say there's something like this, right? So this is a pre-existing chiral center. So if you reacted that with the dienophile, that pre-existing chiral center is going to create a bias when the HOMO and LUMO overlap. And it's going to force one of those products, which like one of the products is going to be favored, one is going to be disfavored, is based on sterics. Because remember when we talked about this at the very beginning, if you take something chiral and something achiral, you're going to get an unequal mixture of stereoisomers. And the only way to get that unequal mixture, if you're trying to generate stereoisomers, is to start with a chiral substrate or use a chiral catalyst. One of the two. But what we discussed, we talked about the catalyst a little, but our main focus was dealing with starting with a chiral substrate. So if you start out with something chiral and you react it with something achiral, then you're going to get a non-racemic mixture. It might not be a huge difference, but one of those products is going to be favored over the other.
Oh, thank you.
Yeah, that's a good question. But in most cases, when you set stereo centers, if you don't have either a chiral catalyst or a chiral star material, or both star materials being chiral, you're going to get a mixture. It's going to be racemic. All right, let's do the next one. And somebody help me out with the arrows. I'll put the numbers in. I can at least do that. 1, 2, 3, 4. Label that. It's 5 and 6. You can. This strategy works no matter what. It doesn't. Like I said, it doesn't matter what your diene looks like. It doesn't matter what your dienophile looks like. You find those 6 atoms that are going to react, and you number them. You can figure out what the product is going to be. All right. So that's the, go ahead.
What, oh, no. What the,
All right. Remember, the reaction is happening between these 6 atoms right here. Nothing else. Not chlorine, not hydrogen, nothing. It's these 6 carbons that are reacting.
okay.
That's it.
The fourth carbon donate to the fifth carbon.
So like, so you're gonna have electrons going from here to here. Is that right? I mean, switch tips. Come on, Russell. Like that, right? And then by default, that pi bond has to break. Otherwise, carbon 5 is going to have too many bonds to it. So that's going to force these where? To here. Is that right?
Then the first one, the pi bond between the first and the second carbon breaks.
It's going to move between 2 and 3. Is that right?
Yes. So
then again, 4 plus 2, we're going to get a 6-membered ring like so. That's sloppy. Come on, Russell. Sloppy right? Pi bond is going to be here. Chlorine is going to be here. And then this is the same 1, 2, 3, 4, 5, 6. Same 6 atoms. The reason I'm saying that is because some of the examples we're going to look at, they are not going to be just simple dienes and dienophiles. The diene is going to be tied up as a part of a larger structure. So we need to be able to recognize that. All right. The last one. What do you think? Anything different going to happen?
no.
For the record, again, it's only these 6 atoms interacting. That's why we call it a pericyclic mechanism. It's limited to those 6 atoms and the electrons flowing between them and nowhere else. So in this case, you'll get a bicyclic system. So this is going to come here like that. That's coming there, and then this is coming here. All right. So I'm going to get a. This is. Let me make these rings a different color. So this back ring, or the ring that you started with, that's still there. They haven't changed it, haven't touched it. None of the atoms reacted, didn't break any bonds there. And then that is going to be here. Now we have another 6-member ring here. Like that. Let me erase all these little. We don't need no confusion about radicals and all that stuff, because not these are all polar processes. Right. So that's what our product is going to look like. It's this is what we call a bicyclic system. So it's 2 rings together. So the bi means 2, cyclic means rings. We got 2 rings together, and this is common. Believe it or not, this is one of the more popular reactions for ring formation. There are a lot of different transformations you can do to generate 6-member rings or to generate cyclohexene derivatives, but this is one of the best ways to do it. It's facile, it's clean. You don't need a catalyst unless you want to make put some chiral centers in. All you need to do is just take your dienophile and heat them up. All right. Let's do. I'm gonna leave this one. Well, let's do this one. All right. It says draw the arrows for the following reaction mechanism between acrolein, which is here, and 2,4-hexadiene. And don't worry about the points. We're not doing that. Right. So how would you show this? So it says here to draw 2,4-hexadiene and a manner similar to the diene shown above. What that really means to draw it in the S-cis conformation, right? And so when you do that, this 2,4 hexadiene is actually going to look like this, where I take this is what the diene here, and then the methyl groups are going to be here. Right? And then that is going to be plus this. Right? So what would the product for that look like?
Would it be a 6 carbon ring?
It better be. It can't be. It better not be something else. If we're doing a cycloaddition, that's the goal, to make a 6-member cyclohexene derivative. So you got these 4 carbons in the diene, these 2 carbons in the dienophile. And we can number them. Like so. And then in the product, we're going to get a six-member ring like that. The methyl groups are still going to be in the same place here. Sorry. So here and here. And that's on carbons 1 and 4. The double bond in the product is going to be here. And then the aldehyde is, if we number these, 2, 3, 4, 5, and then 6. The aldehyde is here. Right, and that is you actually have 3 chiral centers here, right? This is chiral, that's chiral, and this is also a chiral center. But because there's no bias and no way to favor one isomer over the other, then you'll just get a mixture. Can somebody tell me, and this is for lunch, I'll buy you lunch today. It's gonna be a mixture of stereoisomers. How many stereoisomers up am I going to get in that mixture?
Is it 8?
Yes. Was that a beep, like a game show beep? Because you got the right answer.
No, it's my fault.
You got your own beep over there, like you knew the answer was right. Yeah, no, it is 8. So you'll get, and I'll send you a cash out for that. That's good. So remember, the number of stereoisomers is 2 to the n, and you got 3. What n is the number of stereocenters, and we had 3 stereocenters, so it's going to be 2 to the 3rd. I mean, you're going to have a total of 8 possible stereoisomers. So a reaction like this, if you wanted to have one of those isomers favored, you need to do something about it. So you'll probably end up using some type of catalyst with some chirality in it to favor one of those isomers over the other. All right, but you will get 8 different stereoisomers. 4 of them are going to be diastereomers, and then the other 4 be enantiomers of either each other or enantiomers of the diastereomers that you make. All right, let's go to, we haven't talked about this yet, so we'll skip that for now. We'll come back to it. Any questions about what we talked about so far? We'll skip this one too, because that's dealing with the second reaction, but we haven't covered that yet. All right, let's go to number 5. And let me get a volunteer. another volunteer to tell me what the product of reaction number one is going to be. Anybody? I promise you, this class will plead the Fifth Amendment on a regular basis. Before answering the question, how do we? Go ahead.
Dr. Russell.
Go ahead, Diallo.
So it'll be a 6 ring. So those 6 carbons will react. So it'll be well 3 6 rings.
Good.
I guess
3 6-member rings in succession. Is that right?
Yes.
Coming here, here, and then here. Is that right?
Yes.
So the other 2 rings, we're gonna leave them. I'm gonna actually make them a different color, and we're gonna leave them how they are, because they don't react. Only the double bond and that the ring that's towards the front is gonna react. And then the new 6-member ring is gonna be here. That's so sloppy. Come on, Russell. With a double bond here. Is that right?
Yes, sir.
All right, good. What about, let's do number 3, because that's a forward reaction. And we're going to talk about 2 and 4 in reverse, because those are retrosynthesis reactions. What about number 3? Can you see the pattern developing? Like the diene is here, the dienophile is here. And there's only one thing we need to make a note of with the dienophile, and that is that it's trans, right? And that matters because the reaction is stereospecific. That means that in the product, the groups that are on the dienophile also have to be trans. So what would the product look like for that reaction?
That 6 carbon on the dienophile is going to like form a bond with the diene.
So you want to number them here, 2, 3, 4, 5, 6, like that. Is that how you
Yes,
have
sir.
a number?
Yes, sir.
Right. So we're gonna put a bond, and again, I'm gonna put the arrows in because the mechanism is really important. It's simple, but it's important because if you know where the arrows are, where the electrons are flowing, you know where the bonds are going to be made. Well, this is coming here like that. This pair of electrons from the pi bond come here, and then this comes here. Is that what you have?
Yes, sir.
All right. So we're going to get a 6-member ring. Let me zoom in so I can not scribble. Is that right? And then on the 5 and 6 are over here. So we're going to keep the groups on those, but they have to be trans. So this is a methyl group here. And this is an amide here. And then my double bond is going to be there. And if we put the numbers back, 1, 2, 3, 4, 5, 6. Nothing changes. The arrows don't change. The outcome doesn't change. It's just the substituents or the start materials may change. But it's still going to be a 4 + 2 is always going to be between a diene and a dienophile. It's always going to be stereospecific. Now, if you look here, is there another isomer that's possible? Because this is trans, right? But is there another isomer that's possible? Did you say yes?
Yeah.
Yeah, hit your little buzzer again. This is trans, but this is also you can have this also, right? This isomer where the methyl group is on the wedge. And then this is on a dash like so.
I have a question.
Go ahead.
Is that because of the chiral center or this?
Yeah, yeah, and it is also because, and let me see if I can make this plain without going too far to the weeds. When you think about the transition state, right? This is your diene, and this is your dienophile, and this methyl group is coming here, and the amide is here, right? This can approach from the top, or the diene can come from the bottom. Right, there's nothing that precludes the approach from either direction because it's not chiral and there's no chiral catalyst. So the fact that the diene can approach from top or bottom, that means that you have you can get both products, whether the amide is either wedged or it's dashed, just simply because of the approach of the diene. That's a great question, by the way. So it's the approach is unhindered. That means that we're going to get both products or two. All right, what that means is that we're going to get a mixture. And truth be told, most of the time when we present organic reactions, we just give like the main product, but a lot of these reactions you will have mixtures. And when you're in the lab and you're making these, you actually have to separate out the two. These two can't be physically separated because they are mirror images of one another. You have to separate them a different way. But if they were diastereomers, then you could separate them physically, but you can't separate enantiomers physically. But yeah, so because of the fact that the diene can come from either face, then that's going to give you a mixture of products. Let me fix that. All right. Now let's look at 2 and 4 because these are a little different. We have to work backwards. It's a very simple strategy for doing retrosynthesis of 4+2 products. Right? So 2 and 4 are examples of retrosynthesis where we have the product and we work back to the star materials. The strategy is very simple. All right. You always find the cyclohexane ring. So this is the strategy. Find the cyclohexane ring. That 6-member ring that contains the double bond. Once you find that, you're home free. Once you find that ring, you're home free. So in this case, the cyclohexane ring is right here. Right. Once you find that ring, start with the pi bond and start breaking bonds there. So we're gonna take this pair of electrons and push them here like that. We're gonna take this pair of electrons and push it here like that. We're gonna take this pair and push it here. Right. Every bond, it contains 2 electrons. So when we show the arrow coming from the bond here, what we're showing is that bond is breaking. Right. So if I had to, let me see if I can do this right quick. All right, so what I'm literally doing, I'm moving this pair of electrons here. moving this pair here and this pair here, is I am breaking these two sigma bonds here and here. And I'm also breaking this pi bond right here. Let me thin this pencil out just a tad. I'm also breaking this pi bond right here. Right? And I'm making a pi bond here too thick. A pi bond here and a pi bond here. Is that right? That's what those arrows indicate. And that's how I approach the retrosynthesis. I find the cyclohexene ring, and then with that ring, when I break the bonds, because I'm working backwards, I'm always working backwards to a diene and a dienophile, right? Right, so a diene and a dienophile. That's what I'm doing when I'm working backwards like that. So let me take this and put it on the other side of the arrow. Oh, come on. That's the way we can make it work. Right, so this is literally what I'm doing. I'm breaking the sigma bonds, and I'm reforming the pi bonds. Right, so for that particular product, these are the two star materials. That's what the goal of doing a retrosynthesis is, to work from the product back to the star materials. All right, let's do any questions about that? Before we go to number 4.
No, sir.
All right, let's do number 4 then. Number 4, same thing. Where's the cyclohexene ring?
Is it like it's, I don't know how to just like describe it, but it's
Is it here? Oh, let me thin that highlighter out, son. It's too thick. It's here, right? I think this is what you are thinking. I think.
Yes.
It's just, we find the 6-member ring that contains the alkene. Is that right? That contains the double bond. And then once we find that, the strategy is to start at the pi bond and start breaking and making bonds. You're either going to break pi bonds or sigma bonds, and you're either going to make pi bonds or sigma bonds. So let's do that. So let's take this pair of electrons here. And move it to here. Is that right?
Yes.
I'm only touching the 6-member ring. So that bridge where that oxygen is, don't touch it. All I care about is the 6-member ring that I made going forward, which I have highlighted in teal, right? So I'm gonna do that. I'm gonna break this sigma bond here and put those electrons here, like that. And I'm also gonna break this. Well, let me keep it inside. I'm gonna break this and put these electrons here. I did not touch that oxygen bridge because that is a part of the overall structure, but it's not a part, it didn't get formed going forward, right? It was already present. So from that, I'm going to get this. Let me do the Dienophile first, because that's the easiest one. So the Dienophile is going to look like this. Why am I making it trans?
Is it because of the origin of bromine? They have like different stereochemistry.
Yeah, it's trans in the product. And remember, this 4 + 2 is a stereospecific reaction. So if the groups are trans in the product, that means they also had to be trans in the start material, and vice versa. If it's trans in the start material going forward, they have to be trans in the product. So that's the dienophile. And then the diene is going to look like this. Right, like that. Those are my 2 star materials. And if you number the 6 atoms, like we were doing in the other reactions, you number them and put the arrows in, this is the product that you're going to get. That bridge here does not get touched. So that oxygen, we don't touch that, right? It becomes a what we call a bridge head over here. So it's a bridgehead, but it's not a part of the reaction. The only thing that reacts in the 4 + 2 is the diene and the dienophile, and that's it. All right, let's look at 5A and 5B and answer those questions, and then we're going to work through a couple of examples down here, and then we'll be done with this section. And tomorrow, Friday, we won't meet, but I'll just post the exam and you can take it over the weekend. Because I have a meeting I have to be at tomorrow. It's an Friday. It's an all-day meeting, so we won't have a chance to meet. But if you have questions, by all means, just reach out and we can discuss anything you have a question about. All right. 5A says, which product forms the fastest when comparing 1 and 3? What are we comparing in 1 and 3? Because the diene is the same, isn't it?
Yes.
The Dienophile.
The dienophile. So if you look at this dienophile, it actually has a carbonyl attached to it, and this is an electron withdrawing group. Wait, dang it! Come on, Russell. Get my little glove, my little palm protection glove, so I can write the right way. All right, so this is an electron withdrawing group, and if you look up here on this diene or dienophile, sorry, it actually has methyl groups. Well, not methyl groups, but carbons attached to it. So that a carbon is essentially a donor. When you talk about attaching it to an alkene, it becomes like a donor, right? So which one of those is going to be faster? Like, what's one way to increase? We just talked about this too. What is one way to increase the rate of a Diels-Alder cycloaddition?
Having an electron withdrawing group
on your dienophile, right? So 3 should be faster because of the amide. Right. So due to that electron withdrawing group, 3 ought to be faster, right? Compared to 1. And it adds also to draw the second product from the reaction 4. What's the second product going to look like?
Would you flip the stereochemistry?
Say that one more time.
Like invert the stereochemistry.
So instead of the oxygen being on a wedge, put it on a dash.
Yes.
And instead of the bromine being on a dash, put it on a wedge.
Yes.
Yeah, that's exactly right. And again, the reason is because there's no chirality present. So that diene can come from the top or the bottom and with no problem. All right. Let me squeeze in one last example. And then we'll stop. Which one do I want to do? Let's do C. All right. What do you think? If we put the arrows in here and we numbered this, what do you think? Anything gonna change? Is the mechanism gonna suddenly become go through a different path?
No.
No,
No.
nothing is gonna change. I don't care what's attached to your diene, which is here, and what's attached to it, it doesn't matter. Once you find those 6 atoms, that's where the reaction is going to take place. Here, here, and here. It's the exact same mechanism every single time. And I don't want to put in a new page, but I'll just draw this here. These groups are still here. The ester and the chlorine are both trans. So we're going to draw them in here. Oh, I'm sorry, cis. So we're going to draw them in here like this. So that's chlorine. Of course, you can get the other isomer. Right? So all of these are the same. The only ones that that are a little bit more tricky are ones like this where you have 2 rings reacting together. But even that is not impossible. All right. I think what I'll do is I'll post when I post a video, the recording from the day, I'm gonna post like the solution for D, and also work a couple of the other retrosynthesis ones, because these are all retrosynthesis down here. Let's take D, I'm gonna cut it out and put it on a sheet. I'll put it down here. Right, so for D, you can see that the diene is here. Dienophile is here. This is 1, 2, 3, 4, 5, and 6. So when I do the mechanism, I'm going to push this pair of electrons here, this pair here, and then this pair here. I'm going to get a 6-member ring, right? Period. So this is going to be a 6, right? It's going to be connected to this 6. Right? And then the fact that 1 and 4 are connected with a carbon right here, that's going to cause what we call a bridge, right? Right? So that's how that, and the way this would look in 3D, right? Because I know some of the other answers are in 3D. That would look like this. So you have a group here like that. And then, so that's that 5. That's the 5 carbons of your diene. And then that's going to be attached to here. 1, 2, like that. And then this is your 6-member ring. And then I forgot to put the double bond here. And this is what the 6-member ring would look like here, right? So you'll go here, like that, right? And these bonds right here, let me put that double bond back. The bonds here, right? These bonds that are here, they're either going to be wedged. So this is going to be pointed down, or they're going to be dashed where the bridgehead is pointed down. So this will be like, this is also, if we would draw this, it would look like this. So if we would draw it in 2D. So these two bonds right here can be wedged. Or they could be dashed. So it would look like this. Right? Both of those products are possible because if there's no bias, then you can have both products. Right? So something like that, those bicyclic systems, those fused ring systems, those are also possible with the Dienophile Cycloaddition. Now we look at one of the retro problems. And again, anytime when you see these types of structures where you have the bridgehead pointed, that's just a 3D depiction of this. Right? That's all that is. So in this group here, you can see it, since it's underneath the ring, it is going to be on a dash. But anytime you see that bridgehead poking up like that, that's a 3D depiction of this structure right here. Right? The other retrosynthesis, look at this. This is all ugly and big and nasty looking. Doesn't matter. The strategy is still the same for retrosynthesis. Find the 6-member cyclohexene ring, start pushing the electrons. So push these here, push these here, push these here, like that. And so what you'll get as your diene, right? Let me fix that. So that's your diene, and then your dienophile is this structure, right? In the retrosynthesis, those are your two start materials, right? And that's that. For retrosynthesis, same strategy. Find the cyclohexene ring and find a double bond in that ring and start pushing those electrons. All right.